elliptical orbits. So the best way to introduce elliptical orbits in my mind is just to present Kepler's 3 laws that Johannes Kepler formulated many years ago to describe what he was observing when he looked at planetary systems orbiting about the sun, about the Earth. And Kepler's 3 laws can be summarized very succinctly. I'll just write them on the board so that you have them in the notes. The orbit of any smaller body about a larger body is an ellipse with the larger body's center of mass at one of the foci of the ellipse. That's Kepler's law number 1. The second one, I'll just put them all up on the board right now. The orbit of the smaller body sweeps out equal areas in equal times. And 3, the period of the orbit is a function of the semi-major axis of the ellipse and follows this formula. T squared, the same period that we derived for the circular orbit earlier, is actually 4 pi squared a to the 3. I'll explain what a is in a second, divided by Kepler's constant, GMP. And that's it. If you know those 3 rules, you know everything you need to know about in this class for elliptical orbits. Now let's review a little bit of high school geometry just to figure out what these actually mean. Kepler's first law requires you to be able to parse elliptical geometry. So let's do that very quickly. An ellipse has a short side, and then 90 degrees to that has a very long side. The long side is called the major axis. And the short side, 90 degrees to the major axis, is the minor axis. The intersection of the major and the minor axis is called the center of the ellipse. Not to be confused with the foci, which symmetrically are a distance off the center, depending on how eccentric the ellipse is. Now, the first law says that the planet is going to be on one of these 2 foci. There's a focus over here, a focus over here. The planet's going to be one of these 2, and then the body takes this path around the planet. This distance from the minor axis to the end, this is what we call A. We call this the semi-major axis, half of the major axis. And in most textbooks, this dimension, the semi-minor axis, is called B. If you have a measurement of the semi-major axis and the semi-minor axis, you also have a measure of the eccentricity. So eccentricity, E, is a unitless number and when you multiply it by A, the semi-major axis, it tells you what fraction of the semi-major axis do you have to travel down to get to the focus. So both of these foci are EA apart. E is always between 0 and 1. If E is 0, you're dealing with the circle. The two foci collapse onto the center. And what that means is that the semi-major axis and the semi-minor axis wind up being the same. You get a perfect circle. If eccentricity is 1, then you've essentially got a straight line instead of ellipse. You've stretched the ellipse to infinity in one direction. Or equivalently, you've smashed the semi-minor axis down to 0. Mathematically, another interesting property that an ellipse has is that from focus to any point onto the ellipse and back to the other focus, that total length is 2a, no matter where you go on the ellipse. It's a mathematical definition of that particular conic section. Okay, any questions so far? Doing good? Okay, so that's the geometry of the first law. We're going to put the planet on the focus. Whatever orbits that planet has to be an ellipse of some shape. This second one, the orbit of the smaller body sweeps out equal areas and equal times. So here's my planet. Here's the center. My ellipse looks like this. Should be a symmetrical ellipse. Okay, the spacecraft, well, what's actually going to happen here? Okay, so in space, the drag is negligible. So everything actually observes these pristine dynamical equations to a remarkable degree of precision. And what you have is this object that's perpetually exchanging kinetic and potential energy back and forth. As it gets closer to the planet, it's going to speed up because it's giving up potential energy. As it moves away from the planet, it's slowing down. And that's really all that Kepler's second law states, except it does so in a very elegant and quantifiable manner. It basically says if you take an interval of time, just pick any interval, 10 minutes. If I start here and observe the spacecraft for 10 minutes, and I make a pizza slice in this elliptical pizza, and I look at how much pizza I've got, and if I perform the exact same exercise over here for 10 minutes, I get a much weirder looking pizza slice, but it winds up being the same area. And no matter where I make that observation for the same amount of time, I always sweep the same amount of area out. Very cool principle. And you can kind of see why. As the orbit gets highly eccentric, what that's really saying is that up here at the high eccentricities, I'm moving very slowly. So I'm moving very slowly, and then as I come around the back side of the planet, I whip around and come back up. And I whip around and I come back up. Slow down. Now, where is the satellite going to be the fastest? Yeah, basically when it gets the closest. And it turns out the closest point on an ellipse, if we look at our geometry, that's going to be along the semi-major axis over here. And I can even write a formula. V theta, the nice thing about, at this point, the path, the trajectory of the orbit is perpendicular to the semi-major axis. One of the only points on the ellipse that this actually happens. And so there is no r component of velocity. There is only a theta component of velocity. And there's actually a nice little formula for that. It's the square root of gmp 1 plus e divided by the semi-major axis times 1 minus e, whatever your eccentricity is. So that's actually very nice because if you want to code up a dynamic simulator of your orbit, and you're looking for a nice initial condition to give it, you can calculate this pretty easily for a desired orbit, and it only gives you the theta component. There is no r component of velocity. So you can kind of set your simulator into motion at that point and watch it rise and then fall, and rise and then fall. Now compare that to the opposite end. When you're on this part of the major axis, all the way over here, at the highest point, and in that case, my velocity, theta, is going to be equal to gmp 1 minus e over a times 1 plus e. So you see, all I'm doing is flipping the minus and the plus signs. But it makes a big difference. As you get a very eccentric orbit with e approaching 1, my velocity down here is enormous compared to my velocity up here, which becomes very slow. And that's really what Kepler's second law says. Another interesting consequence, we can calculate the entire period for this orbit. But if you actually want to calculate the period from like 0.1 to 0.2, that's actually a challenging computation to do analytically. You usually have to resort to a solver or some special functions that require special evaluations. However, if I want to go from one major axis to the other, 1/2 of a cycle, what's the period? What's the period? Well, remember, equal area sweeps out equal time. So if I go from here to here, and I sweep out this area, and I go from here to here, and sweep out this area, then those areas are the same. They must require the same amount of time. I know that the sum of those two times is a period. They're going to be equal. And so even though it's very difficult to track the time from arbitrary points on an orbit, from 1/2 of the semi-axis, the major axis to the other end of the major axis is always the same, whether you're falling into the planet or you're rising up away from it. That's a helpful formula. I will use that in an example in a few minutes as we work through these problems. Now, I haven't introduced this terminology yet, but these points on the ellipse, when they're applied to orbits, have very special names. When you're at the lowest point in Earth orbit, down here, what is that called? You probably know this already. What's the word we use for that? Okay, aerospace engineers, this is your time to shine. What is it? Periapsis. Oh, you're using the general term. I like it. I like it. You notice how I preface this is I said, what is the closest point to Earth? But he knows the, have you taken the orbital mechanics class already? Oh, nice, nice. You should come up here and teach this stuff. So the general term, when you are at the lowest point in an orbit, that is periapsis. Lowest point. If you are at the highest point, you are at apoapsis. And you will never use these terms again in your life as an electrical engineer. For two reasons. First of all, most of you probably won't go into really hardcore astrodynamic design when you get out of here. The second thing is that you are never orbiting something in the abstract. You are orbiting specific things. And when you orbit specific things, it turns out that you use a different word for each specific thing that you're orbiting. So the most common thing in this class to orbit is the Earth, right? This is where we live. This is where most satellite communications takes place. And in that case, the periapsis is called the perigee. And the apoapsis is called the apogee. You add G instead of apsis. Okay, now this is going to be a technological, it always goes badly when Professor Durgan tries to do something technological. I'm going to attempt in this room for the first time to use the document camera here. I don't even know if I can do this. Let's see. Light. And power. Power is always good. Okay, let's see if we can. Oh, this is excellent. Thanks, Sean. Thank you. Good job. Oh, look at this. It's all framed and everything. This is taken straight out of Wikipedia without shame. So it turns out that everything that you orbit that's different has a different name. You know, this is one of the rare instances when the engineering profession or the physics profession starts to resemble the legal profession. You know, where you take your profession and you enshroud it in some dense, pointless jargon to keep the outsiders out. Look at this. Everything that you orbit, if you orbit the moon, well, okay, let's pick a simpler example. If you orbit the sun, the periapsis is actually the perihelion, and the apoapsis is the aphelion. If you order to orbit something like the moon, you'll notice that there's even like competing terms. Oh, is it the periselene, pericynthian, perilune, aposelene, apocynthian, apolune? Jupiter, perizine, perijove, apozine, apojove. Two different competing. My favorite is this one, the black hole. We've never sent anything in orbit around a black hole. And yet there are three competing conventions. Perimelasma, peribothra, or perinigricon versus apomelasma, apobothra, or aponigricon. I blame the science fiction writers for that one. So be careful. You will probably hear me make this mistake once or twice during the course of this class at least, where we'll be orbiting something other than the Earth, and I'll accidentally call it an apogee or a perigee. Do you aerospace engineers make that mistake too? It's like, you're too kind to say no. Okay, that's fine. So anyway, that's my one use of the document camera. It's about as multimedia as we get in this class. Okay, let's do an example using elliptical orbits. Here's our problem. We've got the Earth, and it pains me to say this, but I once had a student in this class ask me, they say, well, how do they get spacecraft into space? And I had to like pause for a second, and I had to say, rockets. Does everybody know that? You need a rocket to get into space. We'll talk a little bit more about rockets for next lecture, but you launch a satellite into space with a rocket. And all satellites start off in low Earth orbit at some point in their trajectory. They're launched into space. They're beyond most of our atmosphere at that point. Keep in mind that the atmosphere does not magically stop at some altitude, but it tapers off gradually. You know, it gets at 35,000 feet. You already got to pressurize the cabin in your airplane, but it still tapers off quite a ways away, so that you still get residual drag even at hundreds of kilometers above the surface of the Earth. But at some point, you get high enough where the drag is negligible, and you can make lots of stable orbits around the planet without having to re-energize the orbit with propellant as such. And then, if your final destination is one of these higher orbits, at some point you've got to engage another rocket stage and propel your spacecraft to a higher Earth orbit. So, this problem, we are going to start off at R1, a circular low Earth orbit of 1,000 kilometers. And we want to wind up in a medium Earth orbit of R2 of about 20,200 kilometers, which coincidentally, or not so coincidentally, since the instructor engineered the problem, is the altitude of a GPS satellite. So how do we get there? We're orbiting here. We got to jump into this orbit. Well, there's a lot of different ways to do it. Nowadays, people talk about things like ion drives. We've actually have some launches in that where a small, low-powered ion drive that provides very little force but can do so continuously for a very long amount of time with relatively little payload weight, little fuel weight. And in that case, what happens is that you slowly, over the course of days, spiral up until you get into medium Earth orbit, in which case the ion drive shuts off and disengages. And voila, there you are, medium Earth orbit for the rest of the satellite's useful time. There's another way to do it, and it burns more fuel, but what you can do is at a particular point, you fire your thrusters. Maybe just a minute or so, not enough to really move appreciably. It's almost like an instantaneous kick of energy. And that launches you into a higher energy orbit. Now you start off at this point, but you've got more kinetic energy at this point, so you're going to wind up being in an elliptical orbit. And if you time the amount of energy right, you can make it so that your apogee touches the desired orbit that you want to get into. So your perigee is your original circular low Earth orbit, and your apogee is at your final medium Earth orbit. And when you get up here, you got to give yourself another rocket thrust in the backwards direction to kind of propel you forward, thrust you forward, so that you circularize the orbit. You bring your velocity up so that it matches the velocity of the equation that we put on the board 30 minutes ago. For a circular Earth orbit. You're not going to be short of that velocity if you just stay in this elliptical orbit. So with two controlled burns, you can do a very efficient transfer that takes only half a period of the elliptical orbit. Now, this has a special name, this orbital transfer. The aerospace engineers know this as a Hohmann transfer. And so my question to you now is, what's the period? How long does it take to get from this point to this point if I was doing a Hohmann transfer for a GPS satellite? So let's go ahead and figure it out. First of all, I did it again. Look, this is R1. This is a radius. I need to add 6,380 kilometers to get a radius. 1,000 kilometers is the altitude of a low Earth orbit. And likewise, if this is to be a radius, I got to take an altitude, and I got to add 380 kilometers. The word of the problem, which I did not repeat on the board, is in altitudes, not radii. So I've got my two radii, about 7,000 kilometers here. I'm going up to 26,000 or 27,000, 26.5 up at medium Earth orbit. How long does that take? Let's ask a couple questions. How long does it take? What's the eccentricity of the orbit? So we know that perigee is equal to A, my semi-major axis, times 1 minus E. And that apogee is equal to A times 1 plus E. Why is that true? Well, remember, the Earth is going to be at a focus. The centroid is at a focus. The R value, R1, of the perigee plus R of the apogee for this orbit, if I drew it correctly, they should be equal to, the sum of those is twice the semi-major axis. We know this is the center, and E times A, so from this point to the center is A. I have to go another EA to get to the focus, which is the center of the Earth. So 1 plus E times quantity A is my apogee, and 1 minus E, therefore, must be my perigee. And let's see. So if I divide these through, the ratio of these, 1 minus E over 1 plus E, should be equal to 7,380 kilometers for the perigee, divided by 26,580 kilometers for the apogee. Solving for E gives me an eccentricity of 0.56, fairly eccentric. Not too eccentric, but certainly not circular. Now, what is the period? Let's use Kepler's second law. That says T squared is equal to 4 pi squared A cubed over Kepler's constant, GMP for the system. What is A going to be? Well, A, my semi-major axis, is really just the average of perigee plus apogee. So if I average these two quantities and solve for T, what I get, T is equal to 11,000 seconds, or 3 hours and 3 minutes. That's the amount of time it will take to do a Hohmann transfer for that GPS satellite. I should say this is T over 2. Because remember, we only got to go through half of the orbital period to get there. The actual orbital period is 22,000 seconds for that geometry. And then what is the final orbital speed? What is the final orbital speed? Well, that we calculated earlier, right? V theta is equal to the square root GMP divided by your final radius. The final radius is 26,580. This is 6 times 10 to the 24 kilograms. Newton's constant, 6.67 times 10 to the negative 11th. We get 3.8 kilometers per second. So you can see these spacecraft, relative to our observation of the Earth, are actually moving very quickly. They may only be drifting across the sky, but they're moving in thousands of meters per second in order to maintain their stable orbit. It's one of the reasons why we have to launch with such powerful rockets, right? We need giant chemical rockets to get these things into space, because we have to add all that kinetic energy. I mean, relative to the surface of the Earth, we're only moving at a few hundred meters per second with regards to the Earth's rotation. And so we've got to get up to, at least, low Earth orbit. I've got to get into at least 7 kilometers per second, in addition to the potential energy that it takes to get there. So that's a tremendous amount of energy. And I think I'll do one more fun example of an elliptical orbit. We'll do a deep space mission and figure out how long it takes an actual satellite to get to a planet using gravitational slingshots. So let's go ahead and start off with that example. But before that, do we have any questions about previous material? Don't be bashful. If you have a question, then... No? Nothing? Perfect understanding of... Okay. No problem. Now, the trick to get satellite communications to work, of course, is to find these stable orbits that you can put spacecraft. The spacecraft have to be in these stable orbits because this isn't Star Wars. There's not enough energy that you can port into space to have a spacecraft flying around wherever it wants to go, like the Millennium Falcon or something. I once had a reporter from a Canadian news station that was interviewing me, and he said, I think it was about the plane crash, that disappearance of the Malaysian flight that went over the Indian Ocean. He said, well, we're getting these sporadic reports of like surveying satellites. Why why can't we just fly all the satellites over there and kind of look down and look and see what's going on there? And I just said, well, you can't really do that because there isn't a gas station in space, for starters. Any fuel that we need in space, we got to take up there. So it would become prohibitively expensive. We do have to take a little bit of fuel up there to perform station-keeping exercises. So what we're going to learn about a little later today and on next week is there are perturbations and things that we have to overcome so that we stay in those idealized orbits. And that means that we may have to fire the rockets for a little bit once a week to do minor course corrections. That alone, those tiny little bursts and corrections, is usually what limits the usable lifetime of a spacecraft in outer space. So if a satellite lasts 10 or 15 years, it's usually because it can only take 10 or 15 years of station-keeping fuel into outer space. And so that's kind of where we're going. We'll cover more of that stuff towards the end of astrodynamics. When we get into spacecraft subsystems, we'll talk about the power systems and the propulsion and attitude control and RF subsystems and some of the high-level pieces that we have to put together to get a spacecraft functioning. But here, let's go ahead and do a fun thing. Okay. Now, we talked about orbital transfers last time, going from like a low Earth orbit to a medium or a high Earth orbit. And those usually involve firing thrusters. Sometimes you can fire a thruster for a little bit and transfer it using a Hohmann transfer. Sometimes you just blast off. If you're willing to pay for the fuel, you can just blast off and kind of accelerate until you're in the high enough orbital altitude and then circularize with your thrusters. You can do an ion drive where you do a very slow burn that winds your way out to the circular orbit that you need over the course of many days. Now, when you are talking about interplanetary missions, most of those options aren't available to you because even to do things like a Hohmann transfer or a continuous burn is just prohibitively expensive in terms of the amount of energy and fuel you need to take into outer space. We have enough to get out of Earth's orbit to hit escape velocity, and then after that, you're usually wiped. You have very little left. And so we have to think about a way. How do you get to, we know we've done it. We've sent spacecraft to all the planets. So how do we do that? What's the trick? Well, in this class, we study only two-body problems. And then everything else is sort of this non-ideal correction factor or disturbance that you have to deal with. However, the real solar system is a multi-body problem, right? And there's a trick that you can use when you have three bodies to operate against. And it's called a gravitational slingshot. So let's say here's the sun, and here's a planet. The planet is, of course, itself orbiting around the sun in a roughly circular orbit. And let's say that I have a spacecraft. Here's my spacecraft. And draw out a box with two solar panels. That's my standard symbol for a satellite in this class. And the spacecraft is coming in. What happens when it gets to the planet? Well, keep in mind the spacecraft is not orbiting around the planet. It's orbiting around the sun at this point. It's going to accelerate as it gets close to the planet, but it will never orbit the planet unless you do something to the spacecraft, like fire the thrusters and insert yourself into the orbit, because it already has enough potential energy to kinetic plus potential energy to escape the gravitational pull of that planet. So if it comes in, it's not magically going to just start circling around the planet. It will bend in the gravitational field, but it will not insert itself in orbit. And if you line up the bend properly, so let's say the planet is going this way, as this spacecraft comes in, if you let it kind of come around the backside, it will bend. And when it leaves, it will actually have more kinetic energy than what it started with. Now, are you violating the conservation of energy there? No. What you're physically doing is borrowing a little bit of the momentum of the planet itself, effectively. So this planet is moving around the sun. If it was just stationary in space, if this was a fixed system, somehow you would hammer them into the fabric of space and time, nothing would happen. You would basically just change the direction of the orbit, but it would be in the same energy orbit effectively. However, because this planet is moving, it spends more time falling towards the planet than it does flying away. And so you can actually gain some momentum when you do that. And if you are very careful with your calculations, during the exit, you can be in a completely different, higher energy orbit. And so the trick is to take one or more of these gravitational slingshots, piece them together, and hope that the endpoint is the planet that you want to visit or the place in the solar system that you want to visit. So you often hear about these space missions where, oh, the planets are lined up. And you think, oh, yeah, they're all in a row, right? No. It's just that you have to do all these crazy calculations when you have this complicated multi-body system. And there are certain windows in which you can actually get a spacecraft to bounce around to all of these different planets. And that's actually what kind of happened in the 70s when they launched Voyager. It was Voyager 2, I think, the one that went to all the outer planets. The planets were lined up so that you could actually slingshot from one to the next. And then actually out of the solar system as the last hop. So let's go ahead and work an example. Let's just see if after one full lecture of satellite communications, we have enough savvy to plan a deep space mission using gravitational slingshots. So here's the problem statement that we're going to work on. Ripped from the headlines. So at some point in next year, 2016, a spacecraft that NASA launched in 2011, the Juno spacecraft, will reach Jupiter. It's a new science mission to Jupiter. It's called the Juno mission. The launch date was August 2011. And if I could draw a map of the solar system, here's the sun. Here's the Earth orbit around the sun. And then at a higher orbit is Jupiter. Okay. So here's the plan. The spacecraft, when August 2011 is going to launch, it's going to get escape velocity of Earth very quickly. They're going to burn the rockets, get it out of Earth, and insert it into a sun orbit. There's not going to be enough rocket fuel to get an elliptical orbit and do a Hohmann transfer to Jupiter, because your rocket would be bigger than, a dozen Saturn V's or something like that. It would be a prohibitively expensive and risky mission. So instead, it'll be a slightly higher orbit, an elliptical orbit that makes one pass around the sun. And then, unlike a lot of other space missions where you slingshot around Mars or Venus or something like that, this spacecraft is actually going to slingshot off of Earth, the place that it started from, right? Its planet of origin, which will put it in a higher elliptical orbit, and then it'll reach Jupiter. So we have 1, 2 to slingshot. So basically, one full period of this orbit and a half period of this particular orbit. Now, let me give you a couple pieces of salient information Of course, we're going to use Newton's gravitational constant. This is Newton meters squared per kilogram squared. The mass of the sun, you thought the Earth was massive. Check this out. It's about 2 times 10 to the 30 kilograms. When the exponent gets that high, it starts to even be meaningless. Like, you know, it's what is 10 to the 30? It's like the national debt cubed. It's ridiculous. We don't understand numbers that big. Okay. Not quite cubed. 3.25 times 10 to the 11th meters is, I'll put that number up there for a second, our Jupiter. That's the aphelion of this orbit. And in this problem statement, which is ripped from an examination, and the radius of Earth, the mean radius from the sun to its roughly circular orbit, is 1.52 times 10 to the 11 meters. So you see, Jupiter's about, it's a little over 4, well, close to 5 times the distance from the sun that the Earth is. There's a tremendous amount of gravitational potential energy from the sun that you have to overcome to move up there. And so we put it in this elliptical orbit, and I've gone ahead and given you what the aphelion is. Remember, we call it's not the apogee or the apoapsis. The apoapsis around the sun is the aphelion. The aphelion I've calculated for you. I could probably not give that to you in an exam, and you would still be able to calculate it. Okay, so for some reason, some students struggle with this concept of this particular orbit I found in the past. It's a brain teaser, but it's really not that hard. Okay. How many years does it take the Earth to revolve around the sun? 1, right? Okay. So you are launching this satellite, into a higher orbit than that. So you expect to get a number greater than 1. Whatever greater than 1 number you get, it had better be an integer, because the Earth needs to be at the same location that you left it in order to slingshot. You can't slingshot around like a ghost planet, right? And so, however, the higher this orbit is, this initial orbit, the more energy you have to expend to put it in there. So, what is the smallest integer greater than 1 that would make sense to be the period for that first orbit? Don't all tell me at once. The number is 2. The number is 2. This orbital period is 2 years. And let's see, if you averaged these two together, that would give you the semi-major axis. You could actually plug that into your Kepler's second law or third law and calculate the actual period of that orbit, and it would be 2.0. Does everybody understand that reasoning? How we practicing just a combination of common sense and astrodynamics arrived at a period of 2 for that orbit. Yeah, okay. I don't know, there have been some times, I've had some classes in the past that, I think it's probably the way I explain it, that was like, well, why can't you make it 1? Is it because it would never leave the Earth's orbit if you made it 1? So why can't you use 3? Because it's too expensive. Okay, so we already know that this is 2 years. Let's see if we can build on that result and see if we can estimate what is the actual landing date at Jupiter. It'll give us a sense of time for these kind of deep space missions, And we actually do have a projection for when that's supposed to land, and we'll see if we can get anywhere close just using these really simple rules of thumb. Because truth be told, this is probably not exactly half of a perfectly elliptical orbit with the aphelion here and the perihelion down here. But we're going to do an approximation, and I think we'll get pretty close. You can do this, you can look up any old space mission parameters online and do this kind of back of the envelope analysis, and you'll get actually pretty close to how long it took to get the spacecraft there. So, okay, Jupiter's up there, Earth is here. What is the semi-major axis of that second orbit? So that's basically this distance divided by 2, the center of this ellipse. Well, we can say that that one is going to be r Jupiter plus r Earth divided by 2. And let's see here. Let me get my calculator out so I don't do any boo-boos on the board. Let's see, we have 7.78 plus 1.52 divided by 2. So this gives me a semi-major axis of 4.65 times 10 to the 11th meters. And of course, we know that t is squared is 4 pi squared r to the 3 divided by the Keplerian constant. And we just need half of that value. When we add it to 2 years, so 2 years plus this result divided by time should be the total time for this system. If you plug in the numbers that I have over there, you get a total answer of 1.5 times 10 to the 8th seconds. 150 million seconds. Or if you break it all the way down, it's 4 years and 9.2 months. Now, the actual spacecraft will arrive on 19 October 2016. Using that estimate, it should actually be arriving in mid-May of 2016. So we're only about 5 months off, which is actually about less than 10% of the calculation. What would account for the differences? Name some things that might account for the differences. Yeah. Debris. Well, let's say other bodies. Not necessarily debris, but the fact that there are other things other than the sun tugging and changing the gravitational forces on this spacecraft. And over the course of 6 years, those are going to build up into a non-trivial amount of time. Now, we have ways of modeling that are much more sophisticated than I've taught you here in the first lecture of satellite communications. But so you can crunch the numbers and get a much more precise output. Another thing is that we've assumed that these are precisely half ellipses, and that's not exactly true either. We're just using that as an approximation, because usually to make an effective slingshot, you try to line the apogee up with or the aphelion up with the highest point, your destination, and your perihelion with your starting point, but it might be a little bit skewed. The spacecraft also, I think for this particular example, did some rocket burns of remaining fuel in its trajectory to Jupiter, kind of use it up and accelerate the mission or correct for something else. But hey, 5-10%, that's not bad for a back of the envelope calculation. Any other effects or questions? Yeah.
Do we use an equation for t squared? Would it be the total? Are you going to put our here?
Oh, excuse me. Yeah, this would be the mean. I really should write it as A. This is the semi-major axis that we calculated from the previous step. Mean R, or the average of the aphelion and the perihelion, more precisely. Yes?
The orbits of the sun of the Earth in Jupiter circles.
Yes. The short answer is yes. The long answer is no. but they're pretty close. They're pretty close. I think it's like 0.05 or something like that eccentricity for the Earth orbit about the sun. It's pretty reasonable.
Are the orbits on the same plane? Are they slightly up?
The short answer is yes. The long answer is no. they're within a few degrees. The whole solar system does seem to exist on a plane, but there are some disturbances, and what's more, the inclinations will wobble over time slightly because it's a multi-body complicated problem. However, what we found when we do simulations of like lots and lots of particles around an orbiting a large mass, what happens is your first inclination is to think, oh well, everything's just going to collapse in. Like, no, everything kind of stabilizes and makes orbits, but those orbits do tend to arrange themselves into disks, because there's this sort of median gravity that kind of tugs everything to a plane while it's spinning around. So that's why a lot of galaxies you see are these kind of elegant spiral arms, why Saturn has rings, why all these kind of phenomena tend to squash into a plane over billions and billions of years.